circle, any point on the circumference. You've got center. This is where it's rotating around. So I've put theta there. I've drawn the arrow as well to indicate, which is actually kind of important. Oh, I'm missing something. I'm missing a line. To indicate the direction of motion, because I'm thinking angular velocity, and kind of anti-clockwise is our default. Okay, just like on the unit circle. I've got this distance, which is 2. So I've just popped it there because it's useful. All right. So what do we need to work out? 2 questions for this first part. Firstly, angular velocity at A and angular velocity at B. Okay, so what's going on? Let's do A first. A is not so hard, I think you saw that. So this is the angle I'm after in here. Right? So you can see that this angle that I'm after, it's standing on the same arc that this angle is on, except this is the center and this is at the circumference. Okay, so all you need to say is, I guess I would say, PAB, that's going to give me the angular velocity A, right, is equal to theta on 2. And of course your reason for that is angle at the center is twice the angle at the circumference standing on the same arc, etc. Okay. Since it's theta on 2, therefore, because theta, and don't forget, right, this theta dot notation, dot is just differentiate with respect to time.
Yeah.
Okay, so they're just trying to, it's just a shortcut way of writing it, just like we're used to x dot and y dot, etc. Okay, so if this is what that angle is equal to, right, then clearly this is changing, right? So in other words, theta is a function of time, right? So, but this angle is changing at half the rate of this angle, right? So if theta dot's pi radians per second, and this angle is always exactly half of theta, right? Therefore, the rate of change here, or the angular velocity, I should say, the angular velocity at A should be equal to pi radians per second on 2.
Can you just do that?
Okay. Yeah, you can. Okay. Because if you think about it, like, okay, 1 second passes, right? Actually, sorry, start again. Where's a place for it to begin? Maybe here, okay? And then it starts to go around the circle. So where is it after 1 second? Well,
Halfway around.
it's gonna have gone halfway around, okay? So actually your angle here will be, that's not such a good example because I'm actually going to be at A, I think. So let's think about half a second, okay? Half a second. So at half a second, which is actually a good one, I'm gonna need that later. At half a second, I'm gonna have started here, and I'll be up here at pi on 2. Okay, so there's my theta. What will my angle at A be equal to? And you can see you're going to have isosceles, a right angle. Clearly, it's going to be pi on 4 in the corner, right? Which is what you expected. So in half a second, this has moved pi on 2, and in half a second, this has moved pi on 4, right? Which is a rate of pi on 2 radians per second. Okay, so this angle is completely dependent on this angle here, right? And it's changing at half the rate that this angle is changing. So yes, you can just say it, all right? Though you've got to be careful, and the next angle, I'll show you why, okay? So let's have a look now at the next one. I want to work out what's happening at B, okay? So I've written here, this is theta on 2, okay? Now I have some angles here, right? See the angle at P. No matter where P is on the circle, the angle at P, because it's the angle in a semicircle, will be pi on 2 radians, okay? So this is tricky to get, right? This is variable, this is variable, this is not variable. This is pi on 2, and it's always pi on 2, okay? So now when I'm working out an angle like, say, this one, right, how do I calculate that? Well, it's in a triangle, right? But you've got to be careful. It's in a triangle with a variable angle and a not variable angle. Okay, so you have to make sure you don't confuse those with each other, right? So if I want to work out just angle PBA, okay, I suppose I should do it as a proper sum, the angle sum of a triangle, right? So I've got that theta on 2 over there plus pi on 2. Now this changes, this doesn't change. That's going to be equal to pi.
Yeah.
Okay, because of the angle sum of that triangle.
Yeah.
So far so good. Now I want to know what's that angle. That's the angle I'm after, just like I was after it here. right? So when you take everything over to the right side, that'll become pi on 2 minus theta on 2. Okay, so what part of this is changing? And the answer is this part is changing. This part is not changing, right? Therefore, the angular velocity, which is about change, right, at B, depends solely on this part, right? So this is constant. This is the part that's changing, which represents velocity. So it should be minus theta on 2, but theta, its rate of change, its velocity is pi. So it'll be minus pi on 2 radians per second. Okay, so you've got to be really careful about, like, it can get confusing if you think, oh, you know, if you mix these two together and you don't distinguish between them as constant versus variable, right? A common error would be to say, okay, well, when theta dot is pi, then this will become pi on 2. So then the angle should be pi on 2 minus pi on 2, which is 0, right? So you're like, wait, that can't be. The rate of change can't be 0 because the angle is changing as you go around. So the answer is you have to distinguish between these two. Remember that velocity is just about the part that's changing. Okay?